Hi, I'm Vijit, a graduate student at the Indian Institute of Science, Bangalore. In this video, we are going to briefly talk about our recent paper posted on arXiv and also submitted to the MNRS. This work has been done in collaboration with Alankar Datta, another graduate student here, and Pratik Sharma, our PhD advisor. Let's get started. In this paper, we revisit the problem of cloud crashing with optically thin radiative cooling. This is a very well studied, idealized model to understand the interaction between cold dense gas moving relative to an ambient hot medium. The key aim of the simplified cloud crashing setup is to understand the underlying physics needed to interpret the observations and the more complex numerical simulations. Galactic outflows show the spectral signatures of cold gas at high speeds of several hundred kilometers per second, presumably accelerated by the hot fast outflow. However, accelerating cold gas by simply pushing onto it by a hot wind does not work. The cold cloud is mixed into the hot wind well before it can be pushed substantially. A recent breakthrough in this field was made by Gronke and O, who showed that the cold dense clouds can grow rather than be destroyed if they are sufficiently large. They also derived an analytical criterion based on the ratio of the cooling time of the mixed phase and the cloud crushing time for the growth of the dense gas in the cloud crushing problem with radiative cooling. However, recently a work by Lee et al. Came up with a different threshold criterion based on the cooling time of the hot background for the growth of the dense gas. Here in this plot, one can see that the cloud size threshold quoted by Gronke O is lower by at least an order of magnitude. Here K is the density contrast between the cloud and the background in the initial setup, while scripted M is the Mach number of the background wind. These are two important dimensionless parameters of the cloud crushing problem. Our paper seeks to resolve this discrepancy and tries to understand the underlying physics through various diagnostics done in the simulated fluid fields. We run 3D hydrodynamic simulations of cloud crushing with optically thin radiative cooling using the Pluto Hydrodynamics code. We carefully choose cloud sizes in between the Gronkeo and Lie radii. Alankar will present our key results.
Hi, this is Alankar. Thanks, Vijit, for the very nice intro into the problem. One can see the results of our simulation showing cloud survival and growth are in agreement with the Gronkio criteria rather than that of Lee. The colored curves that you see here represent the Gronkio criterion with different Mach numbers of the background wind, and the clouds above this curve show growth but not those below. The black broken line is the Lee criterion, and because we find that there is cloud growth below this line, there is no agreement with the Lee criterion. We analyze our simulation in terms of integrated cloud properties like mass in the dense phase and speed of the cloud material relative to the hot wind. This is one of the important results from our simulation. Here in this plot, one can see that the mass in the dense phase rises for clouds satisfying the Gronkio criterion if radiative cooling is turned on. From the center of mass velocity of the cloud material, one can see that as time progresses, the cloud gets an appreciable amount of momentum from the hot phase and its relative speed with respect to the background wind falls down, indicating entrainment. Now, a natural question that arises is that why there is a discrepancy between all these different works. We carefully investigate this issue and come to the conclusion that the results of the numerical simulations of different groups can be resolved if we recognize that a high density contrast and Mach number of the background wind would imply a longer cooling time of the hot phase. So such simulations must be run longer, which corresponds to several cloud crushing time to test for the possibility of the growth of cold mass in the radiative mixing layer. Lee et al. See the destruction for actually growing clouds because of the combination of a small box size, a high resolution, and their definition by which they identify destroyed clouds. If you have really made it this far, I thank you all for all your patience and listening to us. Really appreciate it. We are happy to receive comments and have discussions. Ciao.